Hello and welcome back to Effortless Mastery. Today we'll be learning on an interesting topic, membrane potential, which will fall under our playlist of membrane physiology. Now, already in our playlist, you can go back and watch them. We had spoken about the cell membrane, spoken about diffusion across the cell membrane. That's how substances are being transported across the cell membrane. Today we're looking at something more exciting, which is membrane potential. And in this particular course of membrane potential, our concern is what occurs to the membrane when an excitable tissue is exposed to stimulus. So membrane potential generally is just what we see as the difference in potential as across a membrane. So whenever you hear the word across means when you compare two different sides of the membrane. So in this case, if I follow inwards, two different sides of the membrane, one is towards the inside of the cell, the other is outside the cell. So now, the potential difference across the things inside the cell and the things outside is what we call membrane potential. And usually when we are more specific, the membrane potential at rest, that is potential difference across a membrane at rest, that's when that excitable tissue is just at rest, is what we call resting membrane potential. Now, resting membrane potential usually has a negative value. And the idea of negativity here is trying to explain the fact that within the cell is more negative than outside. So I'll look at inside the cell, I realize there is negativity compared with outside. This does not mean there are no cations inside. Neither does it mean there are only cations outside. No. Within inside, we have these people that a lot of anions. We have cations. Outside, we have cations and anions. But when we compare them, we realize that if I was to add everybody on the inside and then add everybody on the outside, I'll realize that the difference in their charges will favor negativity inside. So that means if I'm done adding, I'll give an estimate of values. I might end up having, let's say, 10 people here. Then outside, I might be having as high as 70. And when you subtract, you realize that is 10 minus 70 is minus 60. So that is comparing inside and outside, you have negativity of 60. So that is just what it means. So there is always negativity inside at rest. Now, we realize that from there, the next thing is, what are the kind of excitable tissues we deal with? Excitable tissues examples are either neurons, we now look at muscles, and then thirdly, we can talk of glands. So when I speak of the neuron, the resting membrane potential or the potential of a neuron at rest is given by an exact value of minus 70 millivolts. Of course, there might be small discrepancies based on the size of the neuron, but averagely, we have minus 70. For skeletal muscles, we have a range of minus 85 to minus 95. Usually, some books will just capture the average, which of course will be minus 90 millivolts. Now we go to cardiac muscle, which is like an intermediate between skeletal and smooth. Because from basic physiology, we are going to be doing, please don't miss our muscle physiology playlist. It's going to be wonderful and amazing. Now you realize that when we look at cardiac muscle, they are in between skeletal and smooth. So because they're in between skeletal and smooth, we now observe that, okay, they have a potential similar to skeletal, whereas smooth have their own different. Smooth is around minus 50 to minus 60 millivolts. Some books will mention minus 55 as an average. So we come to sinoatrial node. Sinoatrial node is it's an excitable tissue found within the heart muscle. But then his own role is a pacemaker tissue. His own role is not for contraction. So we call him sinoatrial node. And it has a value of minus 60 millivolts. For now, it's just to know these values. The next thing is now, what are the factors? Factors that are responsible for the resting membrane potential of any excitable tissues. There are three primary factors. Number one is the role of potassium leak channels. Number two is the role of sodium leak channels. And number three is the role of sodium-potassium ATPase. Before I progress, I would like to draw your mind to the normal thing we have in a regular cell. We realize that in a regular cell, the fluid inside is called intracellular fluid, and it has more of potassium. But when I go outside, the fluid outside is called extracellular fluid, and it has more of sodium. So if the fluid inside has more of potassium and the fluid outside has more of sodium, the idea of diffusion, which we knew, is that if I have a channel open, that potassium will be going outside, whereas sodium will be doing what? Coming inside. So whenever we open up a channel, potassium will always want to go outside. But when we open up a channel, sodium will always want to come inside. That rule is diffusion. It's a simple idea of diffusion, moving from higher to lower. Potassium is more inside, sodium is more outside. What else must we know? So what will be the role of potassium leak channels? Now, when a cell is at rest, we are taught that the cell is about 100 times more permeable to potassium than sodium. So we just have these channels that are leaky, and those channels, we call them leak channels, will allow more potassium to go out. So potassium is the most important factor among these three factors. Now, usually, it will support potassium efflux. What does the word efflux mean? Efflux means that potassium is going outside. So due to the opening of channels, potassium was more inside to be going out, and it is the most important, the principal factor. Now, like I said, the cell is more permeable to potassium at rest. Now, beyond that, sodium, number 2 is sodium, and this is the most important, the main reason. Number 2, sodium. Sodium can also be leaking in. Yes, like we said, the cell at rest is not really permeable to sodium, but it also plays a small role. And the third one is the person we call sodium-potassium ATPase, probably a person to dwell on a bit. Sodium-potassium ATPase, if you go back to our video on transport across cell membrane, we established that transport can either be through diffusion, passive, or active. And when we talk active, we are talking pumps. We can be talking about primary or secondary. Primary people require ATP, and this is an example. Sodium-potassium ATPase, which is an electrogenic pump. What does it do? Remember we said potassium is more on inside and sodium is more on outside. Ideally, diffusion should support potassium going out and sodium coming in. But this particular guy here is doing the opposite. So at the same cell, he will be taking, instead of bringing in sodium, it will be taking out sodium. As against the normal, ideally, what should be the normal? It is more outside, so it should be coming in. But when I'm now pushing from inside out, that's against concentration, that's active transport. At the same time, I'm pushing potassium in. Usually the exact values is that we take out 3 sodium, but we bring in 2 potassium. When I take out 3 sodium, I bring in 2 potassium. Then this stuff also uses ATP. So it will break down ATP as the source of energy to achieve this. So the idea here is this guy is very important because it ensures that the sodium I was bringing in here, I keep returning it back to the outside. So it helps to maintain the levels of sodium outside and potassium inside. So it pushes 3 potassium, sodium outside, pushes 2 potassium inside, and realize it is against concentration gradients. And what now makes this more beautiful is that if you observe, when I subtract 3 from inside, but then I add 2, what will be my net value? -1. So every single time this pump acts, it gets rid of 3, adds 2. So that means it creates negativity within the cell. So we say this pump is, because of that reason, we say this pump is called an electrogenic pump. The word electro, you are generating a form of electricity or electric potential. Genic is generation. So when you generate something and it's a pump, why is it called a pump? A pump is because it is pumping, it's carrying things against concentration gradients. So we observe. So that is just that. So in summary, resting membrane potential is the potential of a membrane or an excitable tissue at rest. It is the difference in potential across a membrane at rest. Now there are different values for different kinds of excitable tissues, and there are 3 major factors that is responsible for it. Role of potassium leak channel, which will be potassium efflux. Role of sodium leak channel, which will be sodium influx. So sodium is coming in. This other one, potassium, is leaving. And the last one will now be role of sodium-potassium ATPase, which of course, like we said, will always be creating negativity into the cell. Thank you very much for joining us today as we explored this topic. In our next video, we'll be looking at graded potential. That's what happens when there's a distortion to this membrane potential at rest. So please go ahead, like this video, subscribe to this YouTube channel, and ensure you drop a comment so that this video can go to as many people as possible. If you have to share it, please do share it.